intro. Hello all, and welcome to the second lecture of our SciML seminar series. And today we are very pleased to have with us Alex Wadell from Mechanical Engineering, who is going to teach us about tokenization for chemistry. Alex is a fifth-year PhD candidate in Professor Venkat Viswanathan's lab and a meta-research fellow for ARAV battery research. His research is focused on using scientific foundation models to accelerate the electrification of transportation. Using Argonne's Polaris supercomputer, he is currently working to scale up a molecular foundation model to 50 billion molecules to discover better molecular descriptors, which could accelerate the discovery of next-generation energy storage devices. We are very happy to have you with us today, and please take it away. Yeah.
Hope everyone can hear me. Thank you guys for all tuning in. And I think after that nice, wonderful introduction, we're gonna kind of just jump right into it. So to kind of kick it off, the big question here is what exactly is a molecular foundation model and why are we doing it? And the core idea here is that if we can train in an unsupervised manner on a really large corpus of data, particularly the textual encodings of molecules, we're going to be able to learn something about chemistry, which we can then use to develop a really high quality fingerprint of any given molecule that we're given, even if we haven't seen it before. And then once we have that fingerprint, we can then do fine-tuning type tasks using standard MLP to then do basically solve standard regression or classification tasks in material science. So if you want to know what the homoluminal levels of your molecule are, or if you want to know whether or not eating it is a good or bad idea, this type of model would hopefully be able to answer those kinds of questions. And ultimately, if we're able to do this, we're hoping, as we were mentioning, to basically accelerate the development and discovery of electrolytes so we can have higher specific power, high specific energy batteries. You can drive your EV farther, you can take your eVTOL faster, and everything will hopefully be better and will be a bit more electrified. Now, this is not the first time that this has been done. Molecular foundation models have been in the works since about 2020, starting with Camberta, and steadily growing in both size in terms of parameters, but more importantly, perhaps the size of the data sets. And this is largely because there's just so much data. If you just need to do the SMILES strings, you don't need to do DFT or any kind of relaxation to get the interatomic angles or the bond positions. You just need to know how the atoms are connected. And we have pretty standard ways to say, okay, I have this particular atom or this particular compound. How can I add things onto it to get a new molecule? And so Enamine Real Space has produced a massive data set of 50 billion molecules that they are confident enough that you can call them up tomorrow and they'll ship them to you with some charge, of course. Now, based upon that idea, we're going to take that data set of 50 billion molecules, so over an order of magnitude larger than anything that has been trained to date, and we're going to train a new foundation model on it. In particular, we're calling it MIST, the Molecular Insight String Transformer. And to do this, we're using an Insight Award, a Catalyst Award from the MICDE, and we're training our model on currently the 30th largest supercomputer, Polaris. We've just crossed the 9 billion molecule threshold on a model that's 163 million parameters. So we're well on our way to reaching our final target in the billions of parameters and 50 billion molecules. And we're hoping to kind of kick that off in the next few weeks. But even up to this point, we've been able to show pretty exciting results. We're doing at or slightly better than state-of-the-art on quite a wide range of benchmarks, specifically from Molecule Bench, as we can see on these plots right here. And that's the goal of MIST. That's kind of the project that birthed this particular line of research onto tokenization. And that's the last that I'm going to be talking about that for today. What I'm actually going to be telling you about today is about tokenization, which is how do you take this string encoding of molecules and convert it into a sequence of integers. And if we were doing this in natural language processing, there's a pretty tried and true method for doing this. You're going to take your text, you're going to run it through byte pair encoding, where you're going to look at every pair of bytes and see how often do they occur together. And if they occur together frequently you're going to replace that with a single meta token. But in molecules, it's a bit trickier, right? There's not really a notion of words. You just have atoms. There's no real spaces. So where do you split? And what the current state of the art is using is this notion of an atom-wise tokenizer. So instead of splitting on words, we're going to split on atoms. And the way we're going to do that is we're going to take this fun big old regex, and we're going to identify the individual constituent components of that encoding. And we're going to split those into words. And then we're going to look up those little words in a dictionary to assign an ID. So for example, here we have cisplatin. If we were to tokenize it with the atom-wise tokenizer, we break off the chlorine, we break off the bracketed atom, we have our little branches, the chlorine, and then so on and so forth. And then we're going to assign an ID to each one of those unique tokens. We've proposed this new tokenizer called smirk that tries to go a step further. And instead of stopping at bracketed tokens, bracketed atoms, which are captured by this group right over here, we're going to actually split the constituent elements of those brackets further. So here we can see we have platinum and at sp1, so a square planar type 1 chiral center. Here we have our hydrogens. There's 3 explicit hydrogens attached to the nitrogen, so ammonia. And by splitting it up further, what we do is we allow the model to actually do predictions over those features. So it knows a bit more. The downside is that the length of the sequence has increased drastically. This is known as fertility for tokenizers. So it's the average number of tokens per molecule or a sentence or word. And it has a pretty important impact on model performance because the cost of attention grows with the square of sequence length. So if you go from having a single token for an atom to, and the minimum, 3 tokens, the brackets, the element, and the other bracket, or in the case of this platinum, 5, you're going to see a square. So we went from, in this case, 5 to 25x the cost. So a pretty big jump. And it's not really clear that there's definitely research that says that that's not a great thing. You would like a lower fertility. You'd like your tokenizer to be more compressive. In our particular case, because bracketed elements are relatively rare, the overall increase in fertility is minimal. But more importantly, what it lets us do is start doing predictions over those bracketed features. So bracketed atoms are really feature rich. They encode the isotopes, the element, the number of hydrogens there, the charge on the particular atom. And if you tokenize that as a single token, if you change any single one of those features, you have a whole new token. And the model needs to now relearn that those two things are related. If it sees carbon and carbon-12, right, it doesn't know that those are related except for if it sees them occurring together. Whereas with smirk, because we tokenize the bracketed more, it knows what carbon is, and it can potentially learn what that 1, 2 in front of it means. But more importantly here is that because you need a separate token for every single permutation of the features, the requirements on your vocabulary are just truly terrific. Carbon would need at least 75,000 tokens just to make sure you had full coverage of what could be there. It's even worse if you wanted to do the full specification of OpenSMILES, which requires a -15 to +15 charge. Here I'm only showing from 0 to 4, right? If you wanted to start adding class, so you could track the atoms as they move through a reaction, now you have an additional 1,000 tags potentially. So kind of put that number into perspective, 75,000. The entire vocabulary for GPT-4o is 200,000 tokens. That is able to represent all of human written language. And I'm saying I'm going to use about 1/3 of it just to do carbon if I wanted full coverage. And again, these bracketed atoms, yes, they're relatively rare, but they're often really the kind of interesting component of a molecule. I say this as a non-chemist and someone who shouldn't really be trusted to make those kinds of distinctions. However, I really like lithium, and lithium only exists in brackets. And so if I want to make a new battery, I need to be able to represent lithium, and that's important. The entire field of organometallic chemistry is built around bracketed atoms. And so being able to represent them and capture them seems important and a desirable trait in a tokenizer. And so at this point, I think it kind of brings us to the next question here, which is, does your tokenizer know about neon? And the answer is that a surprising number of them don't. If we just look at the support for all elements, so we say we have 118 elements plus an additional 8 aromatics, how many of those can you tokenize successfully without emitting an unknown token? And it turns out for quite a few of these models, not all of them. If we start looking at bonds, for example, these atom-wise tokenizers, so if we look over here, we can see every single one of the bonds is being included, right? So we have our quad bond, we have our ternary bond, double bond, single bond is right there, right? So all 5 of them are represented, plus the non-bond over here. They all have explicitly pre-tokenized to recognize those bonds. Not every single one of them has it in their vocab. And so if you wanted to represent something like gallium arsenic or anything with a quad bond, certain one of these tokenizers, they just can't do it. They can't represent that bond. They would emit an unknown. And kind of the interesting thing here, too, is that while this is like kind of an omission, at the same time, these models are really good. They are able to achieve state-of-the-art performance. They are showing pretty comparable performance and gaining on graph-based models with no geometry, and it's just text. So it's not like they're not good. Part of the issue does appear to be at least the data that's available. If you look at the pink bar, that's MoleculeNet. So that's a common benchmarking set for molecular machine learning models. And you'll notice that almost invariably, even though models don't necessarily, so for example, reaction T5 doesn't know about every single carbon ring token, but it does know pretty much every single molecule in MoleculeNet. I think really what this is it comes down to the fact that these models just aren't necessarily trained and are targeting the full expanse of chemistry, which again, it does make sense. If you don't ever actually encounter the molecule during fine-tuning and pre-training, you're probably not going to be able to give good predictions anyway. So that's where we're at. But smirk, of course, we're able to tokenize everything, but is it an actually good tokenizer? I've already told you that the fertility is increased pretty drastically, that has a measurable and bad impact on the compute cost of these models. So is that whole thing worth it? And how can we kind of evaluate and assess whether one tokenizer is better than the other? And kind of the first thing that we can do here is we can tokenize 1.6 billion molecules, and we can see how often we use each token. And what we find is that you can kind of identify the type of tokenizer based upon their utilization. So all the way over to the left, right here, we can see all the atom-wise tokenizers are kind of clustered together. The next group over here turns out to be a collection of NLP tokenizers. This would be Llama, GPT-4o, Gemma. None of these are designed to tokenize SMILES, but why not? And then kind of the last class that's sitting out all the way over here would be BPE style tokenizers or BPE-like tokenizers that are specifically trained for chemistry. So Converter is using a bog standard BPE tokenizer, but has specifically trained it on a chemistry-based data set. So it's not trained on Wikipedia, it's trained on, I think, PubChem. Over here, in blue, we have SMILES PE, which takes an atom-wise tokenizer and then takes it a step further and starts to learn essentially the co-occurrence of particular tokens and then do merges based upon that. And then smirk GPE is essentially the same thing, but instead of using an atom-wise tokenizer to do that initial tokenization, we use smirk to do the initial tokenization. So we are able to go a bit further. The other kind of thing to kind of note here is that overall, the usage of these vocabularies is limited. So if we're looking at our molecule or chemistry-based tokenizers, each of them have between 29 to 2,000 tokens, with the average being around 600, but we're only actually utilizing about 20 tokens. So we have a vastly inflated vocabulary. That does mean that our model needs to learn how to embed those tokens. So there's a bit of a dead weight there. The flip side is, for example, smirk has 167 tokens. We only, like everyone else, use about 20 when we're tokenizing real space. Partially, that's because molybdenum and all these other interesting components are not necessarily occurring in the data set, and so they don't get utilized. So this is partially reflecting the data that we're training on. But there's kind of like this trade-off here between like you want to have potentially full coverage, but if you aren't necessarily training on it, maybe the token doesn't get utilized and it just kind of floats around in the model's headspace. Okay. So, but at this point, all I've really told you is that some tokenizers use tokens more frequently than others. I haven't really told you about like, does this make it for a good model? And at the end of the day, I don't really want a good tokenizer. I want a good model. So what we're showing right now is essentially a intrinsic metrics for tokenization. So we take a tokenizer, we see how it performs, and we come up with metrics that describe that performance. So for example, fertility. And we say, okay, if we want to lower fertility because that reduces model costs, and that's good. But ultimately, we want to know how are we going to do on our benchmarking downstream performance. And so unfortunately, the way this is typically done is we actually just train an entire language model. You try one tokenizer, you train the full model, you compare it to another tokenizer, and you repeat the process. And the real problem with this is it's really expensive. There's a paper coming out of DeepMind where they looked at different tokenizers and their impact on multi-language modeling. And they literally lament the cost of training and how they weren't able to do more. DeepMind from Google doesn't have enough compute. The other problem here is there's a lot of confounding factors, right? If I train one model and another model with different tokenizers, and I say this one's better because the loss is lower, I mean, yes, but also, did I just do a better job tuning the hyperparameters, right? Was it, maybe this tokenizer is better at this particular width, but if I had a wider model, I would actually be able to achieve better. I'm not necessarily showing you the best model that is possible. I'm just showing you a model. And I want to be able to actually come up with a metric that lets me focus on how good my tokenizer is and not how good my model is at either making up for or covering the limitations of my model. And so what we kind of ended up doing is we turned to perhaps the original large language model, which is an n-gram language model. So instead of training a large transformer or a neural network to predict what the next token is based upon some notion of context, what we're going to do instead is we're just going to count the number of times we saw the previous n-1 tokens followed by this next token. And based upon that, we're going to assign a probability for every single next token. This is pretty nice because you can basically do next token prediction. You can do generative task. It's really simple. We're using add one smoothing. So we basically say the fact that a token exists in the vocabulary is essentially an implicit observation of the token. And it ensures that we never assign a zero probability to any token. There's smarter ways to do this, but they require hyperparameters and fine tuning and more compute, and it starts getting expensive. And so what we can see over here is the predictions that various models would assign to caffeine based upon the models and how they tokenized real space. And overall, they're generally not particularly surprised by caffeine, which makes sense. It's a carbon and nitrogen and a couple of oxygens, something at once. It's pretty standard thing. It's something you see a lot of in real space. And having produced this, we can now actually start to pretend that we have a full-scale language model. So I can evaluate all of my tokenizers. I can train my n-gram language model on 1.6 billion molecules. And then I can go down to a downstream data set, MoleculeNet, and evaluate them and see how well do they perform. And what we find is that, kind of interestingly, chemistry-specific tokenizers do appear to be a bit more robust and essentially generalizable than NLP tokenizers. So you can see that so Transpolymer is built using the Roberta tokenizer with an interesting pre-tokenizer step for chemistry, specifically polymers. And then of course, Llama, GPT, and Gemma are all natural language models. Well, you see they do really well during pre-training, but their loss jumps up quite drastically when we now evaluate them on a different data set. Right. The chemistry models in general, they have a little bit of a variance. We can see smirk goes from being pretty good. It doesn't quite necessarily retain as much of its performance from the other ones, perhaps due to the longer fertility. And of course, over here, we can see SMILES PE. So this byte pair, byte BBE style using an atomized tokenizer does really well. It has a really incredibly low loss. The thing to remember here at this point is that what I'm showing you is the ability of these n-gram models to predict the next token emitted by the tokenizer. I'm not showing you anything that says really anything about the quality of that token. Conceptually, if I had a tokenizer that only outputted the unknown token, I would have a loss of 0, right? But clearly that would not make for a very good model. And we've talked about how some of these tokenizers don't know all of the elements. So how can we evaluate the impact of those emissions? Does it really matter, right? Because conceptually, if you're only missing, say, selenium, right? And selenium only appears in very particular configurations, it doesn't really matter if you emit the token, right? You can just look at the surrounding environment and you can infer the existence of selenium at that point, and the model shouldn't lose any information. Okay, so with that in mind, what we're going to do is we're going to take an input SMILES string. We're going to then tokenize it with each one of our tokenizers, and we're going to identify which tokens would be marked as unknown. So for example, in this case, the model doesn't know about the platinum with an sp carbon configuration. It doesn't know about NH3 atoms, okay? And then we're going to also tokenize using a character-based tokenizer. So we're going to split this into every single character. We're going to train a separate model on that. And then by identifying what would be marked as unknown, we can then marginalize out those characters and compute the difference in the probability assigned to the molecule with and without the unknowns. And that essentially measures the information that we lost by not including the unknown tokens. Now, there's a bit of a downside to this process, which is, as you can see here, the number of characters that are unknown is quite a bit. It's much more than 5. And so as you got a little bit into this model, the context available essentially goes to 0, and it's just randomly guessing. It's a bit unfair, right? If you had a large language model, you would have much wider context, much longer context. And particularly for our model, MIST, we're a bidirectional thing. It's a encoder-only architecture. And so we can see both to the left and the right. And we kind of wanted to be able to capture that. One way to do that would be to train larger n-gram models. The problem is that compute cost grows pretty rapidly with n-gram order, and marginalization grows exponentially with the number of mass tokens. So it gets very, very expensive very, very quickly. And to kind of like combat this, instead what we did was we built a bidirectional n-gram model. So we predict the probability distribution for a particular token based on the joint probability of the previous n-1 and the next n-1 tokens. So essentially, this is mass language modeling with a very old language model. It's kind of cool. And if we do that, we can then actually compute how much information is being lost when we mask out things. So here we're seeing a compound, and encircled in green is the copper and oxygen ions that are not known by, in this case, MolGBT, as well as a few other tokenizers. And we can see that that has a pretty drastic impact on the probability that it is assigning to each token. So here we're seeing how the log odds, so what's the distribution, how that changed from one tokenizer to the other with and without that unknowns. And kind of one thing to note here is like, if we only miss out on the copper ion, we're losing information, right? But it's not necessarily humongous, right? It's 58, and your average is on the order of 58 nats. So it's big, it's essentially a double. Whereas if you say now start losing both the oxygen and the copper, right? Now you essentially have no context in this region. You don't really know what's going on. You have to predict over 3 different atoms essentially. And the impact becomes very rapidly massive. Okay. So this kind of brings us to the final point of the paper, which is that there's this trade-off that we have between how good the model is, or how good we saw that model appeared to be, and how much information it is giving up by not being able to actually represent all of chemistry. And so over here, we can see this is SMILES PE. It is achieving a really low loss, in part because it emits unknown tokens frequently. And so that's not necessarily the most fantastic trade-off to make. Smirk GPE is sitting over, I believe it's here, it's the kind of funky star, and Smirk is over here with the star. It achieves it's a higher loss, right? So it's potentially a harder model to train, but you're not going to lose out on information. You are going to be able to tokenize everything. And the big kind of like trade-off here also is that there's this big question about, do we actually need a chemistry-specific tokenizer, right? Smirk is, and atomized tokenizers are, and I've kind of said that there's some value to that, right? You can actually do predictions over atoms. There's some interpretability advantages there. But depending on your implementation, you really are exposing yourself to this risk of not being able to represent everything. And that's not necessarily fantastic. Of course, there's an easy fix here, which is you could just use a BPE tokenizer, right? You could just use a unigram like Reaction T5 is doing here, and they achieve pretty great results, and they have none of this unknown token problems. So I think perhaps there's kind of two conclusions here, which is that it would be Smirk has a good advantage in that you're going to get a quality tokenization that is essentially identical to the tokenization that you have currently, but you're never going to have an unknown token for a valid OpenSMILES encoding. Or you could just use a standard language processing. You're going to lose the advantages of interpretability that come with atomized tokenization. But it's also just going to kind of work. Transpolymer is right over here. Does really great. And that is literally just taking Roberta, which is a model trained on Wikipedia, and applying it to doing predictions for polymers. And it works. And the kind of the final thing to note here is that there's this trade-off in fertility that we're looking at. And we're able to replicate previous works with our model. So there is some reason to believe that this is at least suggestive of what we'd see downstream once we started training these in an actual language model without having to expend the cost. And up here we have Smirk and kind of the cloud of atomized tokenizers. So you're not really trading off a really large amount of fertility. If you were to say drop down to one of these NLP ones, you would drop your fertility pretty substantially. And hopefully Smirk GPE is letting us kind of do both of those things. You're getting low fertility and chemistry specific tokenization while not having unknown tokens. So that's my talk. I hope you've enjoyed it. And if you want to learn more about this work and kind of what we're doing, there's a paper out. It's on archive right now as a preprint. I encourage you to go check it out. It's fun. And I, of course, would very much like to thank my very large group. We got a good number of them here today, as well as the numerous groups that have kind of funded both myself and provided the truly a massive amount of compute needed to even engage in this work. So thank you. And
thanks, Alex. That was very interesting. So yeah, first, if you have any questions in the room, we can go over them, and then we can go over Zoom. So are there any questions in the room?
How big was your data set?
So 1.6 billion for the molecule net, for the pre-training task. So molecule net, enemy real space in total is 50 billion. We're using a sliver of that, mostly because it just starts getting really big at that scale. 1.6 billion does make these by data set size the largest models for molecules by just a little bit. Moleformer is at 1.2 billion. And then molecule net, the downstream task, I think it's about 200 million in total.
If you were to, I guess maybe this is approaching the internet, but for example, some of these molecules are going to be very similar to each other.
Yes.
And would you be able to say, for example, if there's site mixing or something like that, would your model label them as something new and different, or could it realize that they are the same?
Okay, so you're kind of getting back to the mist and the high. Yeah. So ideally, it's going to be able to learn an embedding that captures that distance, right? So things that are similar chemically in some sense are going to occur close to each other. Things that are really different will be farther apart. Now, part of that comes down to fine tuning. So like the initial parameter embedding that comes out of MIST after this pre-training process is whatever it thinks is helpful in order to predict whatever we've masked out during training. With fine tuning, we can then start getting predictors that say, what are these particular, DFT quantum properties? And yes, we'd actually see similarities there. So
if you remember the ALAB paper from the Sitter group, their model, something that a lot of people, because they had an NLP model to see if, like, for example, a molecule is novel.
Yeah.
And most of them were missing site mixing. This was a bottleneck for their model.
Okay. I'm not familiar with the word, but yeah, no, I think it does kind of come back to this data set. So like the way real space is produced is they start with a set of like input molecules, and then they have a set of reactions that they know they can do reliably, and they build up a data set from that. And so you're not necessarily getting all of the configurations that are possible. And there's perhaps a question of like, is it sufficiently mixed? It's kind of hard to quantify. Novelty is like, nebulous. Yeah.
What's the risk you run of having unknown?
Okay, great question. So I haven't really dig into this, but here we have cisplatin. Cisplatin is a very effective chemotherapy drug. It's on the WHO's list of most essential medicines. It took the cure rate from 10% to 85%. Great drug. The cis variant, so when the chlorines and the ammonias are on opposite sides, is the chemo drug. The trans variant, when they're across from each other, is nothing. Now, capturing that relation requires this at SP1. So if I change that SP1 to an SP2, it switches. So you go from cis to trans. And now you've lost that information. Now, conceptually, you could just do PT, right? Yeah.
Like you do, okay, if it's an unknown token,
sure.
But if you do like a, what you said, like that item wise to,
yeah,
then that's still fine.
No, because okay, so it would be fine if you had a token for platinum at SP1. But because of the just sheer number of combinations, right? So if we go back to carbon, right? Every single variant, there's 60 different chiral configurations that are possible. So for every element, you would need 60 tokens times the number of isotopes, times the number of charges, times, whether or not it was aromatic or alphaphilic, that had hydrogens. So conceptually, if you had that truly massive vocabulary, yeah, you're fine.
So let's say whatever final this thing that you got, that
yes.
So if I take like a subset of that, which I was like, you got to use a bunch of these unknown tokens, then SMILES P should perform.
Yes. I do. Or
yeah. So what threw me off is because you keep constantly comparing SMILES P and
yeah.
numbers.
Yeah.
So that's why I was like confused. Like, what was the risk of whether the risk is
right? Okay. So what's going on here is in the case of SMILES PE, right? They're really good at predicting, or an n-gram model trained on that tokenization is really good at predicting the next token. But if your next token is very frequently an unknown token, right, you can see how that can become easier as a challenge. And so the metric here is essentially being inflated, right? It looks better than it necessarily is. But there's that trade-off here where, because even though the next token is easy to predict, if the next token is unknown, that doesn't really help you learn anything about the molecule. And just to kind of like jump into that point about like their downstream performance, these models do really well. And so they're clearly able to give high quality predictions, even when they are missing out on key information, which is kind of interesting. I think in the particular case of, for example, cisplatin, because you have a stereoisomer there seems like the very real need to be able to talk about those two different configurations, right? And even if the model is able to learn kind of like an average notion of cis and transplanted, being able to distinguish the two is important. Practically.
I had a question. So for basically filling in those unknowns, like can you basically guide the sampling process rather than sampling from the Martian, like do a conditional generation for filling in those unknowns? Like if you can give some sort of geometrical or like additional information about the desirable molecule or something.
So MolGPT has done conditional generation for molecules using SMILES. And there's probably a way to put something like that into an n-gram model. As far as this metric goes, the goal is mostly to replicate what you would see in a normal transformer model and see what would be lost. If you had additional information, yeah, you could perhaps shift it. Realistically, anytime you have more information, right, like you should be able to infer what was missing better.
So how can you encode that sort of information in this like SMILES representation or like atom wise? Like if you have an additional context like that, how do you embed it?
I don't think I understand the question.
Like let's say you have a desirable molecular geometry, something, right? You have a constrained space.
Right.
You want to explore within that space only and fill in the unknowns or something, then how do you embed that?
Okay, so perhaps this is actually it's another really good example. Or let's actually jump to this slide with smirk. So we can see like at SP1, that's one configuration, right? If we got rid of that square planar marker, this would just be a tetrahedral configuration. If we added a few more atoms and spots, we can make this octahedral.
Right.
And so you could certainly start with a skeleton SMILES string and then start predicting, what's the probability of swapping at something in this particular spot.
Okay. Okay. Yeah. Thanks. Like, are there any other questions in the room?
Just one quick one. I think you might have already answered it, but when you were showing the comparison of the cross entropy loss for the enemy versus the molecule net.
Yes.
Basically, the last few ones that you showed, like going from SMILES PE up to Gemma, the performance on enemy for unigram to n-gram or going to 5 gram is basically like kind of almost flipped around when you go to molecule net.
Yes.
So is there some sort of
why is that? Yeah. So generally your n-gram is going to go down because as you have more context, it's more helpful. The problem when you have all that more context is you're potentially overfitting. So when you only have like 2 tokens, you've just seen that combination so many more times. Whereas at the 5 gram, it's a much sparser representation. And if like the objective here was to really come up with a really high quality n-gram model, you probably would start doing better forms of smoothing. So that way you weren't moving as much of that probability mass around with that add one. But then again, that's not the focus.
Any other questions? If not, like people on Zoom, like if you guys have like any questions, you guys can unmute yourself or just post it on chat. I don't think so. Okay. If not, I think that'd be it. Yeah. Thanks, Alex. That was really nice. Thanks for accepting the invitation to speak. And this was really great. So we'll upload this talk like on YouTube later on, if in case like anyone's interested to watch. And with that, thanks again, like to speakers. So thank you.
Bye.